So we had our first lecture last week, where we went through the course logistics and we learned about the machine learning kind of basic principles there. We had the first set of lab sessions last week, and hopefully you're all able to either attend the lecture in person, watch the recordings, or attend one of the lab sessions, or watch one of the lab sessions. Yes, I know it took me some time to upload the lab session recordings. I was traveling this weekend, and the Wi-Fi on Amtrak was not really great. I couldn't really download the whole thing in time, but they have all been uploaded on Monday, so hopefully you had a chance to watch them. That said, is there any questions or comments about how the course is run after experiencing your first week of the course? I knew that how we run the course was pretty much perfect, but not bad. So we learned about machine learning last week because indeed the machine learning is the core of what we do or what we learn in this course, and in fact at the core of the modern natural language processing. And today we're going to move slightly toward natural language processing compared to last week. Because last week, the lecture I gave you last week could very well work for, let's say, the audience of the structural biologists, audience of the music information processing people, audience of the theoretical machine learning people, and so on. It's all the same thing. But today we're going to go into natural language processing a bit further by thinking about how we can build or use the techniques that we have discussed last week in order to build a classifier that classifies any given text snippet into one of the categories. So it's going to be all about the text classification. So in text classification, we need to first define what input is. If you recall from last week's lecture, we've been just assuming that the input is going to be some fixed dimensional vector. In other words, there is going to be just a vector that consists of all these numbers, and every single example that we get is going to have the same number of the numbers. However, what sets text a bit apart from many of those, let's say, classical examples in machine learning or the classification is that now the input is naturally variable length. You probably never see any text that is of the same length for every single document that is written. So we're going to now use the notation that is a sequence. So our input X is going to be a sequence of the first word, second word, and then T many words. We're not going to worry at all about whether each and every one of these is word, characters, or strokes, or bits. We're not going to care about it. Our goal here is trying to abstract us away from the particulars of the particular language that we're working with, and trying to come up with the principles or learn the principles that are equally applicable to whichever language you want to use your system for. Otherwise, we'll have to think that, okay, if W1 is going to be a word, then what does a word mean, for instance, in Chinese? What does a word mean, for instance, in Turkish? It can vary from one language to another. So instead, what we're going to simply say is that, okay, our input text snippet is going to be a sequence of discrete symbols. It's really just that's it. The only thing that we're going to assume here is that each and every one of these discrete symbols, let's say WT, is going to be a member of a larger set of all possible unique tokens or the symbols. And then we often call it as a vocabulary. So this vocabulary V can be a set of unique tokens such as words, subwords, characters, bits, bytes, whatever you want. But from our perspective, we don't really care. During the lab sessions, you're going to see how we have to care about it really, really carefully, but not during the lectures. Now the input length here, T, is going to vary from one example to another. So the length of the sequence is not really determined a priori, but every time we get a new input, we need to look at the length of it. Now, because it's a classification, our target Y is going to be one of capital C many categories. You can imagine that well, can we build a text classifier for the newsroom editors so that whenever they receive a new article from a journalist that report to them, they just fit that article into the text classifier to determine which section that article needs to be published. Or perhaps, we can imagine that we're going to build a text classifier that's going to determine the authorship of any given article. And then that may be able to allow us to determine the authorship of some of the historical documents for which we have no idea of what. And sentiment analysis, one thing that's one of the most popular applications that I don't think anybody should work on anymore, but imagine that if you were working at Amazon, and then there is a new product coming in, perhaps you want to be able to tell whether that product is going to be received positively or negatively by the users, right? So you can try to predict that, categorize the product description into one of the 5 stars. Definitely, I don't think that's a good idea, marketing-wise and so on, but still, you can do that, right? So there are many different problems that we can solve. And of course, we're going to learn about it next week and week after, and then perhaps for many of the lectures throughout the semester. Text classification turns out to be at the core of natural language processing as well as natural language generation. But we'll get to that next week. And because this setting calls for multi-way classification, we're going to look at it from the multi-way classification perspective. Now, if you recall from the previous lecture, what was the multi-class classification? We just define a function f that's going to take as the input one of the input text, right, snippet, and then we're going to look at what is the chance that this text belongs to a particular category. Now, how we parameterize it was to use a vector that corresponds to the particular class y, transpose phi of x, where this one was supposed to be vector, plus b of y, where this was bias. So this bias is just the scalar, but this vector is going to be a d-dimensional vector, where the feature vector is also d-dimensional. Now, once we have this f function, this is a scoring function, we can turn this scoring function into the probability that the input text x belongs to the specified category y. Now, how we did it was to using so-called softmax function. So what are the two criteria you have to, two criteria that must be satisfied probabilities? They have to be non-negative, and then they have to sum to one. I know. I mean, these two are the most important things in the probability theory, and indeed, these are the most important things. And it turned out in this particular case, it's very easy to satisfy them, but in many other cases, it's actually not that easy to satisfy. So in our case, because we only have a small number of the classes, what we're going to do is we're going to exponentiate this score function first. And then what do? We're going to normalize them so that they're going to sum to one. And then we consider all other possible classes. 1, 2, capital C, exponentiate is for the input to belong to that y prime class. And now we get this probability. Now, one thing we want is that last week we did look at it, but we just kind of glossed over it by saying that this phi of x is going to be whatever you do by extracting the features or the important things or the properties about the input that are going to allow us to solve or build a classifier that solves this problem. But today, we go a bit deeper into what this phi of x could be. This is one of the keys today. And before going into getting an actual feature vector, let's talk about how we are going to represent a word. So we said that the input is going to be a sequence of words or symbols or the characters or whatnot. I'll just use words because I started using double so that's kind of the same one of words. We learned that it's just a sequence of words. Now, how do we represent this word? So the one thing that is really, really peculiar about applying these machine learning techniques to natural language processing or natural languages or any kind of, let's say, complex discrete structures is that we actually don't know which of the which pair of these discrete structures or the sentences or the words are similar to each other. Now this might sound weird. Now from our perspective, cat versus dog, pretty similar. I think both of them are mammals, both of them have 4 legs, and both of them have, I don't know, like the tails and so on, right? Okay, pretty similar. Let's say cat and traffic light, pretty different. But then I think let's go with cat and Mars, very different, right? So in our view, it looks like they are very different. But if you think about it, let's say you're given cat, C-A-T here, and a dog, D-O-G there. Okay, so you have these 2 words. How do you actually determine the similarity? How can we determine? You have this intuitive picture of which words are similar with which other words. But if I had to write it down, how I can determine the similarity, what would be the right way to go? So in the case of, let's just come back to, let's think about the age. So every one of us was born at some point, and then what I'm going to say is that I'm going to define the similarity between a pair of people based on how similar their ages are. What would be the natural way to encode this similarity? I'm going to just look at the absolute value of the difference between those 2 numbers, right? The ages. That sounds like a pretty reasonable notion. Height, a similar thing, right? So I'm going to say that, I want to find the person who is similar in height as I am. Then what do I use as a similarity metric? I'm probably going to again use the absolute difference between my height and each of you's height, right? Or the distance, right? So if I wanted to find the cities that are near New York City, I'm going to look at their locations in the latitude and longitude, and then look at the difference, perhaps the Euclidean distance. Makes sense. Now, in the case of cat and dog, what do? We actually don't know. It turned out that we actually don't know how to do so a priori. So without looking at the data, and then even for us, even if we hadn't learned how to speak whatever the language we all speak, then we actually don't know what is the right way to define the similarity. It's just abstract symbols, right? So abstract symbols don't really encode any inherent, let's say, coding system that allows us to compare these different pairs of the entities there. And furthermore, it's actually a very practical matter. Let's say, you're not going to be an English natural language processing engineer or whatnot in the future. You're going to have to use these algorithms to build a system that works for any given language, even if that is very alien to you. So how would you actually build it if you don't know what's happening are in the alien language? And one thing you're going to learn today is that it's actually perfectly fine to not know about those similarities or nor even the language. Because I work on machine translation, I work on the multilingual machine translation, I speak none of those languages by purpose. It's okay. Well, so what we're going to do is that we want to encode this W in a way that does not presume any known knowledge about the similarities among those words. In other words, what we want is that we want the encoding of W to be, so I'm going to use E here, such that given any W and U that are different from each other, I take them, I encode them into some representation, let's say vector, because we love vectors. We encode the W as a vector, we encode U as a vector. When I look at the difference between them, I want the difference to be constant, regardless of which pair of W and U I choose. And one particularly simple way to do so is called one-hot encoding. One-hot, or sometimes people call it one of K. In one-hot encoding, which I'm going to use 1H, this is a horrible way to put it, but let's just put it like that. So the one-hot encoding of this W is going to be a binary vector of the dimensionality that matches the size of the vocabulary. So we're going to make a really large vector where which has as many numbers there are in it as there are words in this vocabulary. And one constraint that we're going to put is that there's only one entry that is 1, and then all the other entries are going to be all zeros. And how do we do that? We're going to say that the ith dimension of this one-up vector of word W. But it's not the first time we're using Zoom, is it? The pandemic has been going on over a year. So it's going to be 1 if this dimension I index is going to be the hash function of W. So we have a bunch of let's say words in this vector. We're essentially hashing it into an integer, right? So we hash it into an integer, and if the hash value corresponds to the dimension, we set it to 1. And then otherwise, what do? We just set it to 0. And then what would be a least interesting hash function? Because the goal here is that we're trying to make the least interesting encoding scheme for a word. It's going to be to simply sort them arbitrarily and then assign a single integer to a single word. In other words, we're going to ensure that the hash of W is not going to be hash of U for all W that is not U. Now by doing so, now let's see if there is a case. So let's say I have a cat, let's say cat corresponding to the index 1, dog corresponding to the index 2. Now cat one-up encoding of cat is going to be all 0 vector except for the very first dimension being 1. Now in the case of dog, it's going to be all 0 except for the second dimension that's going to be set to 1. Now if I look at the difference between those two, what is the difference? It's going to be
1 minus 1.
1, 2, 1, 1, 2, 2. Should it be 2? So if I take the 1 in the first dimension, 0, second dimension, 0 minus 1. If I square each one of them, 1, 1, I sum them, 2 square root of 2. But anyway, I never actually defined which the distance metric we are using. But anyway, so what you notice is that whichever pair of words we are going to choose from this vocabulary after going through the one-up encoding, as long as they are distinct words, the distance is going to be constant. It doesn't really matter which pair you choose. So this is how we're going to encode the words because this is the least informative way to do so. So this is just us saying that we have no idea, right? Which is almost true because there are about 7,000 languages in the world, and any random selection of the language, you're not going to have any idea about the language anyway. So we are going to start with this kind of prior-free, let's say, encoding. And then what we want to do is we want to turn this priorless encoding that is a bit useless because everything is equidistant away from each other into a more dense representation. So this is intentionally sparse, like extreme sparsity, right? So there's nothing but a single element that is non-zero. We're going to turn that into a dense representation. And then how we are going to turn the dense representation is to use it as input to the linear layer that you have already learned from the lab session last week. So there was the NN.linear, right? What did the NN.linear did was to take as input a vector, multiply with a large matrix, and then return the resulting vector. Plus a bias, but that's easy to implement or to subsume into the matrix multiplication. So what that means is that we're going to introduce the notion of embedding. Although to be specific, we want to say that it's a dense embedding and with a couple of the same constraints, but it's actually pretty okay. So we're going to say embedding. And then this embedding of a word, a particular word from a vocabulary is going to be W, the wing matrix, times the one hot vector of this W. So we have a wing matrix. What should be the size of this wing matrix? It should be some d prime rows I. How many columns do we have? As many columns as there are words, right? Is that right? Yeah, sure. So it's going to be R d prime by size of the vocabulary because this one-hot vector is binary vector of the dimensionality that corresponds to the size of the vocabulary. Now, the interesting thing about this matrix vector multiplication is that because of this sparsity and the extreme sparsity, This is same as simply taking or slicing out a one column out of this matrix. So W is going to be, using the Python notation, a slicing of the column vector from this ring matrix, resulting in, let's say, D prime dimensional vector. So, we take a row from W, multiply with this one vector, we only get one value out of it. We do that for every single row, resulting in slicing out single column from this ring matrix. And then this is the reason why often people call this W as a table, and then this whole procedure as a table lookup. So here's a gigantic table. Each row in this table corresponds to one of the words in the vocabulary, and then in that row, which is indexed by this word, has a continuous vector. That is the embedding of the word. Now, why are we embedding this word into this dense representation? Is because in the one space we can't really impose anything beyond the fact that they are all equidistant away from each other. But by pushing this into this continuous space, now there's much more we can let our machine learning algorithm to do in terms of arranging these words so as to capture the similarities among them based on the data. But we'll get to that soon. So now what that means is that we're going to embed each and every word in an input sequence, turning this input X into embedding of W1, embedding of W2, all the way to embedding of W capital T. Now, one thing you might have noticed here is that eventually this phi of X needs to become a single vector, fixed dimensional vector, because the dimensionality of the class associated wave vector Wy is fixed dimensional. So we need to somehow eventually turn this phi of X or the X into a fixed dimensional vector. While here, as you can see, we actually do have T many D prime dimensional vectors. So how do we actually change this into D-dimensional vector? There are many different ways to do so. You can even imagine that this whole course is about how to turn this X, that is a sequence, into a single vector. Today, we're going to just look at one particular example that is called continuous backup. In this continuous backover, phi of X is going to be simply the sum of all these embeddings. So you can imagine why it's a bag of words. We have all these sequences, and then within a single sequence, there could be duplicates, right? So some words just appear multiple times. For instance, those icons in English, like "oh" and "the," they appear multiple times within a single sentence. But then we're simply summing them up. And then what that means is that we're going to ignore the order in which they appear. So a lot of things were well-ordered things here, they all appearing together or the multiple times, once or one not. We're going to just make it into a bag of words. So we're going to just throw them in without ignoring the order of those words. And that's the reason why we call it bag of words. That is continuous because the dense embedding that we're going to use to represent each and every word is continuous for us. We'll learn a lot of advanced approaches. We're going to stick to this for now. Now, let's go back to this, okay? So keep this in your mind. For now. And then we're going to say that even this phi of X, what happens? Then we use so-called softmax classification. So multivariate classification often is called softmax classification just because we use a softmax function in order to turn this course into the probabilities. Then now here, let's look at f of xy, by transpose phi of x plus by just once more. Another way to look at this is to rewrite it as computing a vector A that is the results of the U, a large capital U, so this is a matrix, times phi of x plus b. And then what we do is we're going to take the y coordinate. Now, what do I mean by that? You can build a U to be U1, U2, UC. Because there are as many, so I'm sorry, I'm using U instead of W here, but yeah, just bear with me. So for each class Y, we had a vector U. We're going to simply put them next to each other and then build this large U matrix. And we can do the same thing. Hold on. Should be okay. So let's do this. So we're going to stack them. U1, U2, UC. Then in the case of B bias, it's the same thing. We're going to stack B1, B2, BC. And then eventually, the A is going to be some real valued vector that is whose dimensionality is going to be C, number of the potential classes, all the classes. Then you can imagine that we compute this A and then slice out one score. And then what you notice here is that in fact, what we did here in computing f of x and y is pretty similar to what the table lookup did, right? So we make this A matrix, A vector, and then we're going to look up the corresponding row of the target class, so y, right? It's pretty interesting. And then what you get here is that how we score each class, or whether the input belongs to each class, is essentially trying to look for the class embedding of this U matrix that is a table, and then compare that against the feature of the input. Yes, very confused. Oh, okay, so very confused. Sorry, that's not that great. But all right, so let's try it again. So let's go up here. Now, what was this embedding? The embedding of the word was to look at this W, that is a table. It's a very large table. How many entries are there in this table? As many as there are words in this vocabulary B. And then we took out one row or the one vector that corresponds to the particular word that we're looking for, that is W. Okay. Now here, if you think about it, what does this UI does? If you think about what UI does, is that we have a table of class embeddings. How many entries do we have in this U matrix? C many entries, right? Because there are C many classes. And then we're going to slice out one row that corresponds to the Y, the class that we want to evaluate the input against, right? So that's why it's quite similar to, in fact, embedding. So we're finding a class embedding, and then given the class embedding, we're going to look at how well this class embedding corresponds to the input feature P of X. What this says is that at the end of the day, it's all the same thing because the classes as well. No one told us which classes are similar to each other. Let's say I have a news article, let's say a section classification problem. And then somebody told me that, okay, here's a section A and here's section B. How similar are those sections? We don't know a priori, right? We don't know a priori without looking at the data. So it's the same thing in a sense that the embedding that we talked about of a word is same as the embedding of the class. At the end of the day, it's all about how to represent these discrete entities, be it an input symbol or be it a classes, into some, let's say, continuous vector representation that allows us to capture, or not us, no, we're not going to do that, allows our machine learning algorithm to capture the similarities. So we'll continue to do this. These are row vectors. You can imagine like it really doesn't matter. You can always flip it, right? So the dimensionalities often don't really clash. But yes, row vectors. All right. So let's rewrite it with this in your mind. So let's keep in our mind that we're going to use the continuous bag of words. And we're using this softmax or the multi-class classification. I'm going to write out f of xy. Oh, so I have the uy transpose and sum that goes from T1 to capital T, embedding of WT plus dy. because it's a summation and then the vector product or the inner product of the vectors is just linear, we can just push this u, y inside. In other words, we're going to look at the t, the summation going from t1 to capital T, uy transpose E of wt plus v1. I'm going to just make one assumption. So assume that your dy is just 0. It's just a bit of a nuisance, and it doesn't really matter that much. We talked about what this bias does already last week, so we're not going to talk about it, but we're going to say that it's all 0, which is same as saying that marginally, without looking at the data, we have no prior, let's say, preference toward any one of those categories, but every category is equally likely when we don't look at the data. That's the point. Now, once we write it like this, what you notice here is that the score of x belonging to a particular class y is a sum of how well aligned each and every word that constitutes the input x against this, the class embedding. So what you're looking at is that I have a class embedding. So let's say I have a sports embedding. So it's the sports section of the newspaper. And then I have all the words. I'm going to have the word that says MLB, pitcher, catcher, the homer, whatever. And then we're going to look at the class embedding, word embedding, look at how well aligned they are, right? That's what the dot product is computing. And then we just sum all those scores, all those alignment scores. Now, this is interesting in the sense that in this regard, to which class would any of the input belong to or deemed belonging to is a class that has this embedding that most align with as many words as possible in the input. Then we'll see how we actually get down. So up to this point, what have we done? We have worked on the parametrization of a model. So before we go into the learning part, any questions so far? Yes.
When you're embedding the classes, the initial assumption that we have for the embedding of x, and the difference should be constant. Does that also always work?
Yes, that's already there because you can imagine that we have the one hot embedding of the class, and then we multiply that to u, and then we're going to slice out the class embedding. So yes, the fact that we are using this U matrix tells us that the classes are a priori assumed to be equidistant away from each other, and we're going to embed that class into a continuous vector space using this U matrix or the table or word embedding, whatever you want to call it. Any other questions? All fine? It's either my teaching is super clarified over the past, let's say, 5 years, or that it's gotten to a point that no one can understand. I'm not sure which direction, but two extremes all meet with each other. Yes. All right, so then now we're going to move on to learn. Oh, there you go. Yes.
I was wondering if you're summing the embeddings over the how many words are in the sequence, wouldn't that cause it to basically be distorted for longer sequences versus shorter ones?
Yeah, so that's a really good question. So one thing that is a bit weird about this continuous back of word is that we only sum, right? And then if you imagine this, let's say I have an article that talks about, say, baseball. So it should belong to the sports category. And then I have another article that's also talking about baseball. That should belong to the sports category. And then both of them are talking about the baseball. But my classifier, but let's say the second article was 10 times longer than the first article. Then my classifier is going to suddenly tell me that probability-wise, or they look at the score-wise, the second article is 10 times more likely to belong to the sports section when it is not the case. However, there's one issue is that it depends on the application, because I can think about another example where the length matters. Let's say I decided to write a classifier that's going to tell us about the quality of a review that was uploaded for some product on, let's say, Amazon, right? One thing you know is that if the review is like 2 words long, you know that that is not the review that you want to show it to the other customers. The length of the review actually does tell us quite a lot about the effort that they have put, in which case, perhaps the length matters. So this is more of a decision that needs to be made based on the problem itself, what is the right way to encode it. And then that is the reason why last week we didn't talk at all about fee. Because what we said was that the decision on how to build fee has to be determined based on the problem that you're solving. Now, in this particular case, continuous backup works, we assume that the length of the input articles are more or less similar. So they're going to be not too distributed over, let's say, huge range. And in which case is okay. So, but that's a good point. Some people use the average of embeddings as well. All right, any other questions?
Just to clarify the class embedding matrix, it's one hot coded or?
So you can imagine, it's the same thing, right? So the encoding a class or word as the one encoding and then pass it through the linear layer is identical to simply slicing out a row or column of a matrix. Right? So we don't explicitly do this. We don't do it explicitly, but it's done implicitly when we compute the score for each and every class all simultaneously as a matrix multiplication. So the U times the feature vector phi of x. All right, so now let's try to do some learning here. Now, what is the first thing we need to do? We need to define the loss function. And what was the loss function we're going to use? We're going to use a negative loss probability of the correct class to which the input belongs. And minimizing the negative loss probability, identical to maximizing the loss probability. So we're going to think about the maximizing the loss probability of the correct label y star given input x. That is, we need to write down the low probability of the correct label y star given x. And if you just write it down, you have the u y star transpose phi of x. We're continuing to assume that the bias is just 0 minus log of the partition function of the normalization constant, that is summation over all possible classes. And it's the exponentiated score. So dy transpose phi of x. So this is same as the score assigned to the x and y star, and this part is going to be log z of x. And what we want is to slowly increase this quantity by changing this class embeddings. We have C many class embeddings. And then what was the technique that we were going to use? Gradient descent, right? Gradient descent. And in particular, we were going to use the stochastic gradient descent, which is same as simply taking a small subset of the training examples, compute the per example gradient of gradient, and then simply sum them or average them. What that means is that all we need to look at is to compute the gradient of this single per example log probability. For this one, I want to actually look at 2 different things. Let me see. I'm just trying to figure out the order in which I actually explained. Oh yes, okay. So we're going to start with the word embedding. So there are 2 things we can update here. One is class embedding. 2 is the word embedding. E of W. Okay. Let's see what we can do about it. The first thing we do is to compute the gradient of this quantity with respect to phi of x. Phi was a feature of the x that is a continuous back over, so we're going to compute the gradient of the log p of y star given x with respect to this thing, this p of x. Then if you just derive it carefully, you end up with this equation. uy, which is identical to uy star minus y given x uy. Now let's look at this for a second. So what is this gradient? This gradient tells us how to change this phi of x, the feature vector, just a little, so that after that update, the low probability of the correct class y star is going to increase a bit, right? And then what is this? This turned out to be the difference between the class embedding of the correct class. So this is a class embedding of the correct class minus the expected class embedding according to our model. So according to the current classifier. Let's say current classifier has the probability distribution such that the peak is at the another class, not the correct class. Then this one is going to be dominated by the incorrect, let's say, embedding class, right? But what does that mean? That means that the feature vector at the moment is aligned so much more with this incorrect class embedding. So what we do is that we are actually pushing the feature vector away from this incorrect class embedding and push it toward the correct class embedding. Okay, kind of makes sense. If you took the intro to machine learning, which I think is prerequisite, this looks quite familiar. Should look quite familiar to you. This is a perceptron learning rule in some sense. It's a software version, but it's a perceptron learning rule. That is that given an input, you're trying to add the embedding of the correct class while you subtract the embedding of the predicted class. If the predicted class is same as the correct class, they disappear, they cancel each other because the learning is over, right? The prediction is correct, we don't need to do anything. But if the prediction is incorrect, then we're going to move the feature vector a bit so that it's going to better align with the correct class embedding. Okay, so this is one thing, but this doesn't really tell us how to update the word embeddings because the phi of x is not the word embedding itself, it's the sum of the word embeddings. What that means is that we need to look at the Jacobian of this gradient. So we need to look at the Jacobian of this gradient with respect to each token embeddings. Now, because this notation is going crazy, I'm going to just revert to the partial difference derivative notation. So we want to look at the Jacobian of this gradient with respect to one of the embedding vectors. So we have this gradient that tells us what is the right thing to do in terms of feature vector, but then I need to know what does that correspond to in terms of changing the actual word embedding, individual word embedding, one of them, right? And it turned out that very conveniently in this continuous backover is simply just the gradient is. In other words, the gradient of the low probability of the correct class with respect to the embedding of one of the words in the input is same as the gradient of the same thing with respect to the feature vector x, phi of x. So we're going to use the very same thing. What this means, what does it mean? Is that we're going to look at one of the words in the input. Let's say it was baseball, right? And then the correct class was sports. But the current model says that, okay, it belongs to art. And what we're going to do is that we're going to add the class embedding of the sports to the word embedding of baseball, and then subtract the class embedding of art from the word embedding of baseball, so that the word embedding of baseball is going to be better aligned with the class embedding of sports, and less aligned with the class embedding of art. And then when the learning is done, then already prediction is going to be about sports. And then this one is going to be sports class embedding. This is going to be sports class embedding, no learn. So how confused are you? If you're not confused at all, raise your hand. It's okay. No shame in not being confused in a lecture. Okay. We're not in high school anymore. So yes. If you know something, you can say that you know.
Could you you explain the partial derivative of the gradient again?
This one, yes. So let's go. So we are computing. We are trying. Oh, wait, hold on. Okay, I'm sorry about that. I will. And this. Okay. Yes. Does that answer your question? No.
How does that do?
So what I actually wanted to do was this. So what I wanted to, so if you remember the chain rule, so let's look at the log p of y star given x, and then what we want to do is computing this. And then if you think about the chain rule of derivative, it's going to log p y star given x, derivative with respect to the p of x, and then the Jacobian of the p of x with respect to e of yt. And then because it's just a sum of all these word embedding vectors, this is actually just identity. We end up with the original thing as is. Sorry about that. I just brushed through too many steps and then I made a mistake. So it's confusing, but this line should be less confusing version. How is that though? No one actually, I mean, they said that they were confused because there were clearly a mistake there. Any other, okay.
So the reason that happens is because we're using this continuous stack of words.
Yes,
You know,
yes, because the p of x is a continuous back of word, and then if you're trying to compute the partial derivative of this, the outcome of the sum of many terms with respect to one of the terms, that's just the identity or the one.
Would you mind just repeating what you said again?
Mhm.
Like where you said, I think it was that you're subtracting the embedding of, you're taking the embedding of the correct class and subtracting the embedding of
Right.
the
Yes.
words. Yeah.
So let's say I have a sentence that contains, t many words, and then each and every word has its own embedding, right? That's going to be EWT, right, for each and every one of them. And then what I want to figure out is that how should I change this embedding vector in order to increase the log probability of the correct class y star. And then to do that, we compute the gradient of the log probability of the correct class y star given x with respect to the embedding of individual words, because we should update them. And then what is the direction toward which we change this? Is that we try to make it better aligned with the y star's class embedding and less aligned with the expected class embedding. That is that what is the expected class embedding according to our current classifier? If it predicts perfectly the y star, then this expected class embedding is going to be identical to u of y star. So they cancel out, meaning that, prediction perfect, nothing to do. If our classifier says that another class is more likely, this UI is going to be not like UI star. So we try to make the EWT more similar to UI star, but less similar to the class embedding of the prediction. So how we actually get the word embedding of this, let's say, baseball related terms to be similar with each other, because the embeddings of all those baseball related terms will have to be aligned better. Will have to align better with the sports class embedding. So that's how the learning happens. Is that we look at the word embedding of each and every one of them. We look at how well this word embedding aligns with the class embeddings, all the classes. And then we try to make sure that this word embedding is going to align best with the correct class embedding. And then that automatically falls off by just writing down the gradient.
For the distinction between a word embedding and class embedding, so baseball would have a class embedding sport, but what would be its word?
So the word embedding of the baseball will have to be very, very similar to the class embedding of sports, right? Because that's the only way in which the log probability of sports will be really high when the baseball was in. But then it cannot be just same, because baseball may be used in an article that belongs to another drama. Right? Let's say some scandal by a baseball star. That's a baseball, but it should, let's say, belong to the entertainment, let's say, section. Then this baseball word embedding needs to align really well with the sports embedding, but also with the entertainment embedding. But probably not, shouldn't align well with the art embedding. That's right. Yes.
How are the class embeddings learned?
That's exactly what we're going to talk about now. Yes. So this is really, it can be confusing, but it's very important concept because this is how, if you think about it, if somebody gave you the perfect class embeddings, this is how you're going to know that the words that appear frequently in an articles that belong to the same class will have similar word embeddings because they have to align well with the same class embedding, the one embedding that there is. Okay, so this is how our model, by just following the gradient of the loss function that automatically was defined based on what we learned last week. That's how this model, this machine learning algorithm is going to figure out which of these words are similar to each other by looking at whether they appear together in an articles that belong to the same class. But anyway, but that is assuming that we got this amazing class embeddings, which may not be always doable. So let's talk about the class embedding. So let's see. So the class embedding is going to look pretty similar, as you can imagine. But what we are going to do is we're going to look at the gradient with respect to the correct class embedding first. UY star.
Gradient of B.
Sorry?
Gradient of B.
Gradient of the low probability. For example, low probability is P of X minus X of UY star T transpose P of X over sum Y prime go from 1 to C except of UY prime transpose P of X. And then P of X, which is same as saying that the P of X minus P of Y star minus X P of X, which is same as saying 1 minus P of Y star X P of X. So this just comes from the fact that this quantity here is the softmax of the score that is given to the Y star, right? So that's how we get the probability of Y star given X. And then we have the feature vector of X both sides, so we just combine them, and it becomes 1 minus P of Y star given X times a feature of X. And then you kind of, let's say, see that, okay, what happens here? Let's say my classifier was perfect. My classifier is perfect. So the probability assigned to the correct class given any input X is perfect, as in 1. Then there's nothing to learn. Learning has been done, right? Because it's already 1 minus 1, 0. If my classifier is horrible, so that it has put a very, very small probability to the Y star, then we're going to have a quite positive value here that is multiplied to the feature vector of X. What that says is that the class embedding of the correct class UY star is not aligned with the feature vector of X enough, so we want to make it as aligned as possible to the feature vector of X, P of X. So that's when we look at the correct class. Now let's look at the incorrect class. In the case of incorrect class, that is not Y star. So here Y is not Y star. Then what we end up with is X of UY transpose P of X over sum Y prime equals 1 to C X of UY prime transpose P of X. And P of X, it can be rewritten as a minus P of Y with X, P of X. It can now be rewritten as 0 minus P of Y with X, P of X. It looks pretty similar to the previous one, except the fact that it's now 1 plus 0. Now you can imagine this 1 and 0 as a target. So what is the desired output for this probability assigned to this class Y. If Y was Y star, the correct one, we want it to be 1. If the Y was not the correct one, we want it to be 0. So then but let's say our model was horrible and then assign too much probability to this incorrect class. And what happens is this becomes a very large negative value. It's multiplied to phi of x. So we're going to subtract the feature vector of input from this incorrect class embedding. So that the incorrect class embedding is going to be pushed away and then stop aligning too well to this input feature. So what this means is that the class embedding is also the result of relying on the word embedding. So the class, what would be the perfect class embedding in this particular case? Is that it has to be some kind of average or average of the most frequently occurring words in that class. So in the case of the sports embedding will have to be very, very similar to the word embeddings of all those sports related terms. Art embedding will have to be very, very similar to the art related terms. Otherwise, if that is not the case, then the article that talks a lot about sports will be assigned to art, and then art embedding is going to be pushed away from that one. Yes?
So are word and class embeddings simultaneously trained?
Yes, so that's actually the interesting point. We looked at the word embedding and the class embedding, how they're learned separately, but what we do is we actually update everything all simultaneously. So we estimate the word embeddings, we estimate the class embeddings all together. And then what ends up happening is that we learn both the similarities among the words as well as the similarities among the classes all simultaneously. Okay. So far so good? Yes?
So initially there wouldn't be any class effect or only one star.
Initially, we're going to just initialize all these embeddings to be some random number. Drawn from some Gaussian distribution with a reasonable standard deviation. Yes.
So does this all mean the number of dimensions you need in phi of x is logarithm log of the number of words?
So does it mean that the number of dimensions we need, so for the say the phi of x be the log of the vocabulary? No, that doesn't actually say that. So you're thinking about how to compress them, but the compression does not actually tell us about the similarities. Maybe some of the words are identical, right? So maybe we can just push them all together. Right? At the end of the day, what you really need is that the dimensionality. So the dimensionality of this kind of word embedding or the class embeddings need to be determined not only based on the kind of information theoretic criterion or whatever the criterion you can think of, but from the perspective of the generalization that involves learning as well as inference. And then in this particular case, it can be as large as you want. Sometimes higher dimensionality, you get an easier learning. Sometimes with the higher dimensionality, there is an implicit regularization effect that it gets you a better generalization. So there is no the answer to choose how to choose the dimensionality. Now that said, we're going to take 5-minute break, and then we'll come back, and then we're going to finally finish the lecture. So please come back in 5 minutes. All right. Okay. Right. Oh, so for one thing, there were some questions about the quiz. Weekly quiz, we're going to release it on Monday morning. So like the 9 a.m. or 8 a.m. And then the deadline is going to be, I forgot exactly, but I think the 5 p.m. on Friday. So we're sticking to this kind of, let's say, 40-hour a week work hours. So that you won't have to worry about the quiz during the week. So so the first week quiz is going to be released in the morning on Monday, this coming Monday. And then you will have about 5 days, right? 4.5 days or so to complete it. There won't be any limitations on the number of submissions you can make. There won't be any limitations on how the hours or anything like that. Well, grown-ups, you do what you need to do in order to answer all those questions and submit it, and we're going to grade it as well as we can. Any questions about the quiz?
What form do the answers take? Is it like
Various forms. Yes. Some multiple choices, some free-form answers, some I think we might even have a bit of a coding, as in not you don't put the code, but you're going to ask to run something or implement something, run something, and then report the results. But that's kind of, let's say, free-form answers. Yes. So various kinds. Yes.
So little cards, but basically it's just assignment.
I don't know. I look at the first quiz. It's already prepared. I look at the questions. They are super easy. So I don't know. I guess that's supposed to be for me. But anyway, it's going to be. Yes. Any other questions about the quiz? All right.
Yeah.
Oh yes.
Will the question in the quiz become super hard in the future?
Yeah. So the first one, but we haven't actually created any further quizzes. So I can't really guarantee that it's going to get easier or harder. But it's okay. Again, the point here is not to make a very difficult quiz question so that it's going to be much easier for me at the end of the semester to just sort all of you into one line, and they have to say that, oh, A, A minus, that's not the purpose. The purpose is to let you learn. So,
Wait, Professor Cho, is the coding like in PyTorch?
yeah, so whatever the programming that you're going to experience during the lab session or whatnot is all going to be doable on Colab using PyTorch.
Discussion is allowed.
Sorry?
Discussion between students is allowed.
Sorry.
Discussion between students is allowed.
Yeah, go ahead. Talk to your peers. But when you type the answer, just type it yourself. That's the same thing, right? So, discuss with your peers. Yeah. Again, the purpose is not to make sure that I fail some of you. I don't really care. So just making sure that you all kind of understand. If you talk with your peers and then you learn something, that's good. That's more. All right. So let's continue. We're going to spend the next, let's say, about half an hour talking about the limitations of linear classifiers. So what we have learned so far is called linear classifier. It is considered a linear classifier because the score we get here is a linear function of the input that is a word embeddings. Right? So the input was a sequence of word embeddings. All we do is we're simply computing the weighted sum of them across multiple dimensions and then sum them again. So that's why this classifier is linear. And then such a linear classifier is simply not powerful enough. Let's imagine an example where you want to build a sentiment classifier that's going to read some kind of review and then try to determine whether that reviewer was happy or unhappy about the product. Right? And then what you assume is that the word embedding of a word hate is going to be very well aligned with the class embedding of negative class. Word embedding of word love is going to be very well aligned with the class embedding of class positive. Right? Kind of makes sense, right? Based on what we have just learned, that's exactly what's going to happen. And then yet, if you think about it, okay, how about not? So negating something, if I just think about it, it sounds like something that's going to should align well with the negative sign. So the word embedding of word not probably will align well with the class embedding of negative. But what if our review had not been paid? Then it probably should be positive because it just negated the negative sentiment. And obviously you can make the same example of not. Unfortunately, capturing that kind of relationship. That is, that if there was a love, should be positive. If there was a hate, should be negative. But if there was a not hate, should be positive again. Not love, should be negative again. Is pretty much impossible with a linear continuous backup word classifier, because the effect or the impact of individual words is additive. You can't really cancel things out easily. You can get lucky in a high dimensional space and you can cancel some of the things once in a while, but strictly saying that is not guaranteed to happen in general. So the linear classifiers are not powerful due to its nature of being able to only accumulate information, but very difficult to avoid, let's say, remove the existing information, or in other words, the inability to capture the higher order interactions beyond just the first order approximation, that is that whether this word exists or not. So what we need to do is we need to go into the nonlinear classification. That is, we want to ensure that the relationship between the input, that is a sequence of word embeddings, and the output is going to be nonlinear. I'm going to make up a very weird example and then show you that with the nonlinear classifier, we can solve this problem of not hate, not love, and the hate and love all together by creating a neural net manually. What we're going to do is we are going to say that our vocabulary consists of only 3 words. 0 is going to be hate, 1 is going to be love, 2 is going to be not. And then our classes, so Y is going to belong to either positive or negative. And I'll just put some assumptions saying that the word embedding of each word is going to be normalized. So it's going to be always a unit length in Euclidean sense. And the word embedding of the hate and not is orthogonal to each other. And also word embedding of the love and not is orthogonal to each other. And then because we're working in a pretty high dimensional space, it's very easy to satisfy this kind of constraints. So that is one of the reasons why we don't want to constrain ourselves to minimum size model. And perhaps unsurprisingly, we are going to say that the embedding of the love is same as the embedding of the hate, except for the sign. So these 2 embeddings are going to point into the opposite direction. Right, that makes sense, right? So love and hate kind of pointing into the opposite direction. But again, if we are building a nonlinear classifier, tough love could be actually close to the hate. Okay, we'll get to it. I'll do the manual learning and then we'll. And then what we're going to do is we're going to introduce a hidden layer. Now we're going into the realm of the deep learning. It's going to be a tiny deep learning. We're going to go to a deep learning where we have a hidden layer that has the 4 hidden neurons. So HI is going to be, let's say, we're going to use a rectified linear unit. So max of 0 and the beta times WI transpose I goes from 1 to 4. So it's a tiny hidden layer where I have the 4 neurons. Each neuron has its own weight matrix, WI, that is going to be multiplied to the input embedding or the phi. It can be phi or E, doesn't really matter. And then there will be some small, let's say, value that I'm going to use that is called beta. And then if this value is greater than 0, and we take this value as it is, if this value is negative, then we're going to simply set it to 0. So it is still nonlinear. Yes.
How are you defining?
Oh, we'll talk about it. I'll do it manually. So if you work on artificial neural net for about 10 years, then you get this ability to train a neural net manually as well. You'll be surprised that it is actually true. So for each of the neuron, I'm going to assign the weight vector myself. So the first neuron's weight vector is going to be same as the embedding of 8. The second neuron's weight is going to be the embedding of love. third neuron's weight is going to be embedding of hate plus fourth neuron's weight is going to be the embedding of love plus embedding of. So this is going to be our neural network. And then we already set everything essentially in some sense. Right? Now, what I'm going to do is let's look at what happens to the activation of these four neurons in the hidden layer. First case, case one. What if the input was just hate, right? If input was hate, then H1 is going to be, let me see, so I'm going to use the sigma in order to just make it a bit easier to write. It's going to be sigma of beta, H2 is going to be sigma of 1 minus beta, and H3 is going to be sigma of beta, and H4 is going to be sigma of 0. Because of all these assumptions, you can just write it down later, but you have to, unless I made a mistake, which is very likely, but still, it's easy to fix if I did so. Let's say my input was not low. The H1 is going to be sigma of minus beta, H2 is going to be sigma of beta, H3 is going to be sigma of 0, H4 is going to be sigma of 2 times the beta. Now, third one is going to be not hate. H1 is going to be sigma of beta, H2 is going to be sigma of minus beta, H3 is going to be sigma of 2 beta, H4 is going to be sigma of 0. Okay. And then the fourth case is that what if the input was love? H1 is going to be sigma of minus beta, H2 is sigma of beta, H3 is sigma of 0, H4 is going to be sigma of beta. Now, with this choice of the rectifier linear units and the choice of these weight vectors and everything, we can now write it down as the actual number. Now, in the case of hate, we end up with the beta 0, because this was a negative, we just suppress it. Beta is going to be any positive constant. Not love is going to be 0, beta, 0, 2 beta. Because there was a 2, and then it's just a linear function. 2 beta, a sigma of 2 beta is just 2 beta. Not hate is going to be beta, 0, 2 beta, 0. And then the fourth one, the love, is going to be 0, beta, 0. So these red colored ones are going to be the activations we get from the hidden layer we have. So if the input was just hate, we're going to have the beta, 0, beta, 0. When the not love was the input, it's going to 0, beta, 0, 2, 0. Not hate, beta, 0, 2, beta, 0. If the input was love, 0, beta, 0, beta. Maybe you're already sensing where I'm getting here. But once I have this, I can now set the class embeddings myself. Class embeddings for the negative case should be 1, minus 1, minus 1 over 2, and then the u of positive should be minus 1, 1, 1, minus 1 over 2. So where did these numbers come from? So these numbers actually come from the fact that now we're going to do exactly what we did earlier. Instead, only thing that changes is that we're not looking at the phi of x in order to change the class embedding. We're going to look at this output from the hidden layer in order to determine what the class embedding should be. So the class embedding of the negative should align very, very well with the hate and not love. But it shouldn't align well with the not hate and love. On the other hand, the class embedding of the positive class should align really, really well with the love and not hate, but it shouldn't align well with the not love and hate. And then it turned out that the vector set I just wrote down does serve that purpose, is that the u negative that is going to be 1 minus 1 minus 1 over 2 and 1 aligns better with the hate and not love hidden activation compared to the others. And the negative and positive, the same thing, but with the not hate and love. Yes.
So this one has to be flipped.
Which
like
one?
the negative one being the fourth position and the positive one the third? If not, why not? Two beta is in the fourth.
Let me see. So the two beta, and the fourth one, because I want to, the positive one is going to cancel the two beta, so that it's going to cancel out there.
Well, but aren't the bottom, like the not hate, the love one is the positive?
Not hate is the positive, yes. So let me see. If I just compute, if I compute the dot product between U positive and let's say not hate, I'm going to have the minus beta, and then plus 2 beta, and that's going to be beta, right? Okay, and then I'm going to compute the dot product between U positive and let's say not love. Then it's going to be beta, and then 0, and then minus beta, so it's 0. So this one is better aligned with the not hate than not love, right?
Gotcha, okay.
So yeah, how it does is that these hidden neurons, 1, 2, 3, 4, are working together in order to make a pattern that allows us to separate out the not from love, hate from not hate. So that's what this kind of nonlinear layer does. So it detects all those higher order interactions that cannot be captured by simple summations. It allows us to build a much more sophisticated classifier that captures all those as a complicated relationship. Even if the input was backup words, by having these nonlinear layers, we can build a very powerful classifier. So this actually tells us a lot about the importance of building a nonlinear classifier over the linear classifiers. And then the fact that the parametrization of the network and feature representation, these two serve two different roles. So our feature representation was super simple. It's a sum of all the word embeddings, but by making a nonlinear parametrization, it works better. But you can imagine that you can do something different as well. You make the feature, the representation better to encode all those orders, and then build a linear classifier that's going to do as well as this nonlinear classifier. Yes.
So the not love, you're just multiplying the representations by not and love together. I think that how you.
Oh no. So not love is so the here input is going to be the sum of the not embedding and then love embedding. Yes. So that was the input, but then you had this is the output from the hidden layer. It took as an input the continuous backward, and then outputs this kind of vector. So this actually tells us a lot. Is that when we build this kind of machine learning system for natural language processing, we have to really think about every possible aspect that you can imagine. All right, any other questions about the importance of the nonlinear classification or the nonlinear parametrization? Of course, other than the fact that you have to how I was able to come up with this example like this. Because you have to thinking a lot. Yes. So what this actually tells us is that it looks nice, but it's increasingly less convenient to train this kind of model as the number of layers grows. Right? I mean, it's not like I'll be able to come up with a ways for, let's say, a network that has 100 hidden layers. I think the 2 hidden layers, I might be able to manage a bit, but your 100 is going to be difficult. And then what we're going to learn over the course of this semester is that the number of layers in the models that we use to handle natural language text can be considered as many layers as there are in the words in the sentence or the paragraph or the document. So we're going to build a neural net that's going to be thousands of layers deep, and then there's no way we can actually do this for the 1,000-layer deep network. And this is where the idea of the backpropagation comes in. It's almost unnecessary for me to talk about backpropagation, unlike, let's say, in 2015 when backpropagation was still not being taught in machine learning courses. But nowadays, backpropagation is the first thing that they teach. But we're going to go over the backpropagation just once more, because it turned out that the backpropagation tells us a lot about what kind of behavior a loss function that we have defined exhibit. And then that actually informs us how to design a model parametrization or the loss function so as to avoid any of those pitfalls or the degeneracies in the loss functions. So we'll go through the backpropagation basis just quickly, 10 more minutes, right? So let's look at the nonlinear text classifier once more. We can rewrite it as the f of xy. So it's just a multi-class classifier, right? As a uy transpose phi of x plus cy. So it's the class embedding, classifiers. And then instead of just saying that the phi of x is a bag of words, continuous bag of words, we have some non-linearity, sigma, of w, some weight matrix, times the continuous bag of sigma.
The kind of UYT5 plus.
Sorry?
The first line F, capital F, X, Y, one UY.
Uy transpose phi of x plus cy. C is just bias, okay? Which we, briefly assume to be 0, but we don't have to. And then so let's see where this W comes from. W comes from stacking all those hidden neuron specifically. Right? We had the W1, W2, there was dot producted into the input that is the continuous back of word. But what we are saying is that so this continuous back of word was a d-dimensional vector, and then we're going to multiply with this weight matrix, add the bias vector, and then apply the element-wise nonlinearity to end up with d prime dimensional hidden activation, right? So this nonlinear hidden layer is going to give us a d prime dimensional vector, and then accordingly, the class embedding dimensionality changes to d prime dimension. So we are kind of, let's say, disassociating the dimensionality of the word embedding and dimensionality of the class embedding now, right? So it becomes a bit more complicated than before. Then the question here, we already know how to compute the gradient with respect to the class embedding. That doesn't change, same thing, because it is still linear at the very end. But the question we have is how do we compute the gradient with respect to this W matrix? The input to trying to adjust the weight vector associated with each and every hidden neuron. That's the big question. So how do we compute gradient with respect to, let's say, each and every, so I neurons weight. So you can imagine that here, let's just look at it. You can imagine that we have the H1, H2, H3, H4. Then we had the input, there was a phi of x, there's a continuous back over. For each neuron, we had the associated weight. And then we computed the dot product, we got some score out, and then we applied the nonlinearity on top of it. So here, we can say that, okay, what is the gradient of the low probability of the correct class connect with respect to the I neurons weight vector? So we're going to write it. It's going to be a bit of a pain, but just bear with me. Let's see. So what we want is that we're going to say gradient of the. I'll use L as a shorthand for the low probability of the x, y, then W here, and we follow the chain rule of derivatives. So we look at the partial or gradient of the loss or the low probability with respect to the output of the hidden neuron. So this is going to be output from the hidden layer, which is this. And then we need to look at the Jacobian of this output of the hidden layer with respect to, we need to look at the gradient, the partial derivative of the non-linearity. So this is the non-linearity. So that's going to be sigma. So maybe I should have used sigma. And then we multiply with the Jacobian of the input to this nonlinearity, which is A is this whole thing with respect to the weight matrix W. It's just a chain rule of derivative. Of course, it's not the usual derivative because these are some of them vectors. So then you get the Jacobian and all those things. But as soon as we get the dimensional, if you transpose correctly, we can just say that we can do it. So we're going to just write it like this for the purpose of convenience and the easiness in interpretation. Now,
Sorry,
yeah.
was A,
Now,
yeah, the hidden layer output.
A was going to be the hidden layers output right before the nonlinearity. I was going to write it. This is A. All right, so then let's look at each term in this chain. So the first one, E of A, we already know, we looked at it already, right? It's going to be the difference between the class embedding of the correct class and the expected class embedding under our model's prediction. We all know. So what this tells us is that before we're talking about how to change the word embedding, it tells us what is the change that needs to be made to this hidden activation that came out of the hidden layer to make the low probability of the correct class greater. And then let's look at the second one. Let's move to the A. And then this one is going to be, in fact, diagonal matrix, where the diagonals correspond to the element wise, let's say the derivative of the non-linearities. If we assume that we are going to use a rectified linear unit that is the max of the 0 and the input, then this becomes prime IA is going to be 1 if AI, let's say the input is going to be greater than 0 and then 0 other. Right, so because we had this. So if you use the max of 0 and the input as the nonlinearity, then its derivative is going to be either 1 or 0, or the sub-bracket because it's not really differentiable, but it doesn't really matter. Okay, so far so good. So what does it tell? What does it tell us? What it tells us is that it tries to check which one of the input or the neurons were contributing to the prediction. So for any neuron, before applying this rectified linear unit, any neuron that responded positively contribute to changing the output of the prediction. Any neuron whose contribution or the response was negative doesn't contribute because we have the max 0, right? So we cut it up. So this is what this term is, tells us that. And then this term tells us a lot about the nonlinearity that we use. And then the third one is Jacobian of the A, that is the response of the hidden neuron. So right before the nonlinearity with respect to W. Unfortunately, this one is easy because it's just a linear function. Just a linear function. What we end up with is WT transpose. Now, what it tells us is that this just tells us that how much influence this input embeddings have. So you can imagine that by chaining these 3 steps, we're going to start by looking at, well, let's see what is the right way to change the hidden activation. And the right way to change the hidden activation is to make it align better with a correct class embedding and misalign with the incorrect class embedding. But then how do I know how to change it that way? I need to figure out which of the neurons were actually contributing and then which ones are not contributing. If I look at those ones that were contributing ones, then what were the embedding vectors that were contributing to this high, let's say, level of response? So that is how we're going to propagate this error in the prediction all the way back to the weight matrix before the nonlinear hidden layer was applied. And then that is the reason why it's called back propagation. So we're back propagating the error signal by looking at the Jacobian at each of the layers. And then the Jacobian tells us who should be blamed or who should be credited in order to make the value, the output, the loss to be smaller or low probability to be higher. So that's why some people call it credit assignment procedure, back propagation, just chain rule of derivatives. There are many ways to call it. And you can also view it as solving some kind of dynamic programming. That's for the later, let's say, discussion. So is there any questions about this kind of manual back propagation procedure that we have just done? And then what it does in order to increase the low probability of the.
So if a neuron was only ever out basically negative A's, would it ever have its weights updated?
Very good question. So any neuron who did not contribute, its weight vector is not going to be updated for this individual example. But the thing is, that's the beauty of this machine learning, or in some sense compressing the data, is that these hidden neurons are going to be used for many different examples. Some examples are going to activate it, some examples are not. And then what we look at is that we're looking at some kind of this average difference. So the answer is that the individual neurons, yes, for the individual example, yes, if the neuron was dead, associated weights are not updated. If you look at a data set, most of the neurons are associated weights are updated, but you're right, there are quite a lot of, let's say, neurons that end up just completely turned off across all those examples. That does happen. We can just prune that. Not too deep. Any other questions? All right, so if not, then you notice that this is still very cumbersome to do so, right? Then already in 90s, Jan LeCun and Leon Boutou, actually in 80s, knew that this whole procedure can be largely automated. And then in fact, there has been a whole field that is called automatic differentiation that has been working on how to automatically compute this gradient across this complicated function that can be characterized as some kind of directed acyclic. So we start from the input. There are many different variables of which we, with respect to which we want to compute a gradient, and there's a single output at the end. And then you can imagine that this is directed acyclic graph. If there are cycles, of course, it's not really well defined to compute the gradient. So we're going to say that we have a directed acyclic graph. And then what you notice is that what we are solving at this point is to look at some function that's going to take as input, some input, and then large number of the parameters, and then push it into some, let's say, target value. This is just going to be scalar. Now, what we do is to compute the gradient of this G with respect to parameters. So this G is just a directed acyclic graph that describes a computation that is done by our classifier all the way to the loss function. So this is going to be output of the loss, this is going to be loss. Then what we're trying to compute is the gradient of this Y or the G with respect to theta. Now all we really need is to know how to compute this and G of, sorry about that, I actually completely messed up. I used the wrong notation. Let me rewind. So let's say I have a function G that takes as input some input, and then it has some parameters, and it's going to output not the loss, but some kind of output, right? And then let's say we know how to compute the Jacobian of this G with respect to the parameters theta, as well as the input at any given point, right? So at any point in time, I evaluate G in X and theta. So any given value, I evaluate it, I got Y, and then I'm going to assume that I know how to compute the Jacobian of this output with respect to the input, as well as the parameters. And then what does this Jacobian compute is that it's the sensitivity. What is a way to change the input so as to change the output? That's what the Jacobian tells us, right? So it's a kind of gradient there, or the derivative. So an example would be, let's say I can have a linear G that is going to take as input X, and then the parameters are W and V, and then the output is going to be W times X plus V. So this is going to be a linear function. We can also write a very simple one, such as a rectified linear unit, which is going to take as the input, then there are no parameters. And it's going to simply return the max of 0 and X. Then we can have this, all these blocks. And then all those functions that we've looked at so far, in this case of, let's say, nonlinear multiplex classifier, you can imagine that, oh, we have a linear function here. We have a rectified linear function here. We have another linear function here. We can have the softmax function there. We have the log function there. And for each and every one of them, we know how to compute this Jacobian with respect to the parameters if there exists one, and then with respect to theirs. And all we need to do is to build a neural net or the classifier by combining these building block functions. One step at a time. We build a directed acyclic graph. And then at the end, we're going to have a loss function. And then given this, we just follow back, starting from the end all the way until the beginning, to compute the gradient of the loss function with respect to every single parameter. And then all we needed to do was to implement each and every these basic building blocks and the Jacobians that are associated with it. And then it becomes just automatic application of the chain rule of derivatives. And that does conclude today's lecture. And we will meet next week. Yes. If you look at the quiz, we have a lab sessions tomorrow in the afternoon.